Alright guys, so this is our second Flip the Classroom lesson for Chapter 6, and in this lesson we're going to talk about an alternate way to define a point's position on the plane. And normally when we're defining a point's position on the plane, we use the Cartesian coordinate system, or the XY axis. And when we're talking about a point on the XY axis, we define it by its horizontal and vertical position with respect to the origin. So right here we might have some horizontal position on our x-axis A and some vertical position on our y-axis B, and together those two coordinates come together to give us the ordered pair AB, which defines the point's position with respect to the origin. Our ordered pair AB could also be referred to as a pair of rectangular coordinates because the horizontal and vertical values that come together to give us that ordered pair can create a rectangle between that point and the origin, right? So that's why we call them rectangular coordinates. Now, as we're defining our point's position with these rectangular coordinates, it's worth asking ourselves, is this the most natural way to define the point's position? If I were sort of talking about how to get to this point, would I naturally say I travel some horizontal distance A and some vertical distance B to get to this point? And actually, if we think about it, probably our most natural inclination is to say, no, actually what I would do is I would turn from the x-axis to face the point, and then I would travel a more direct distance to that point, right? Now, right here, what we've basically done is defined the point on the plane by a rotation theta from standard position and a distance we'll call r that is a direct distance from the origin to that point. And this is defining the point with what we call polar coordinates, r theta. And what we're going to talk about today is the polar coordinate system, or the polar plane. So right here, the polar coordinate system is a coordinate system where points are defined by a distance from the origin r in a direction theta defined as a rotation from standard position. So we've got distance from the origin r in a direction theta, which is a rotation from standard position. When we're on the polar plane, we call this point the pole, and we refer to it as O, and it corresponds to the origin, the point 0, 0 on the xy axis. We call right here this line the polar axis, and it's going to be the initial side for all angles that are going to define our points, or the direction our points are in. And it corresponds obviously to the positive x-axis because it's a rotation from standard position. When we're talking about points on the polar plane, we basically have a distance r in a direction theta. So right here we call r the directed distance, and we call theta the directed angle. And in general, what you want to think is a point is basically going to be a distance in a direction. So right here, we're looking at the point 3 2/3 pi. We would first rotate 2/3 pi and then go the distance of 3 in that direction to define the point on the plane. Now, right here in general, what we'll say before we plot this point is theta is generally going to be our input and the r value will be our output. So unlike the x and y value, the input comes second in these polar points. So right here, what we want to take a look at is first the rotation of 2/3 pi, and our grids are pretty much always going to be set up the same for the polar plane. Really what we're going to see is rotations in increments of 30 degrees, or pi over 6 radians. And if we're looking at this, basically what we're seeing is we've got all the stops of the unit circle except for the half quadrant stops, so the stops that are 45-degree increments or pi over 4 increments. And right here, if we're defining this point, what we can say first is we would rotate 2/3 pi and say that's the direction the point is in, and then we would travel 3 units in that direction to get to the point. So right here what we're talking about is increments of radius, or maybe units of radius. So right here we would say 1 unit of radius, 2 units of radius, 3 units of radius takes us to our point, 2/3 pi, right? And that's how we would sort of get to that point. Now, our sort of angle of rotation and the distance that we've traveled to get to that point, we want to remind ourselves that those aren't actually part of the graph, and that in the end, hopefully we're getting to the point where we can just sort of plot the point instead of thinking as much about it. So right here, we can go ahead and talk about some other points we can plot. In general, what we'll say is that the directed angle theta could be positive or negative, right? And that's pretty natural from standard position. We can rotate up for a positive angle and down for a negative angle. But we also want to take note that the r value itself could be positive or negative, and we're going to talk about what that means in a second. So let's first plot this second example A. Right here, what we're saying is that our point is a distance 1 in a direction negative pi over 6 from the origin. So right here, first what we'll do is rotate from standard position down pi over 6. That's that angle right there. And now if we're looking at a distance 1 in that direction, that's 1 unit out, and that gives us our first point, A, right there, right? If we want to go ahead and plot the point B, we first have to rotate 225 degrees, which is 45 degrees past 180, so that would be a rotation that takes us all the way back around here, right? And we're halfway into that third quadrant with this rotation. Now right here, since our r value is negative, what we want to think is that we, instead of moving forward 3 units, we're going to move backward 3 units. So basically, we've rotated to the direction of 225 degrees, but we're not going to be moving in that direction because our r value is negative. We're going to be going in the opposite direction 3 units. And when we go in the opposite direction 3 units, we actually get this point right here in the first quadrant that we would say would be our point B. So that's plotting points on the polar coordinate system, or the polar plane. And what I want you guys to do right now is to go ahead and pause the video and try to graph these 3 points, A, B, and C, that we're seeing right here. So give these 3 points a shot. All right, so these are the 3 points we're seeing. Let's go ahead and talk about how we got to these points. So right here with our point A, we're looking at a rotation of 3/2 pi, so that's a rotation all the way around and onto the negative y-axis. Now right here at this point, what we're going to do, since our r value is positive, is we're going to travel 4 units in that direction. Now, we're traveling on the negative y-axis, but don't be thrown. Remember that all our points are really defined by rotation and then a distance in that direction of the rotation. So it's going to take us down 4 units to that point right there, right? Now for our next point, we are talking about a distance of -2 in a direction of 150 degrees. So we rotate 150 degrees, which is all but 30 degrees of 180 degrees. So we've got that last stop right there in the second quadrant. Now right here again, we're looking at a negative r value. So basically right here, what we're going to say is we're not traveling forward in that direction. We're traveling backwards, which is going to take us back into the fourth quadrant right here for our point. If we look at our C, we're traveling a distance of 3 units in the direction of 8/3 pi. Now, 8/3 pi is a rotation that is more than a full rotation, or 2 pi. And what we can think is that this is actually a distance of 3 in the 2 2/3 pi direction. Now we can evaluate that full rotation of 2 pi. And then from there, what we're going to do is evaluate our 2/3, which is an additional 2/3 of a rotation. And that'll take us right there into the second quadrant. And now what we're going to do is travel a distance of 3 units in that direction, which takes us all the way out to that point right there. So again, what we've done right here is basically sort of map out how we got to that point. Again, we're not really going to be drawing these rotations and these lines when we plot our points, but it's worth it to sort of like visualize it in this way at first. All right, so let's answer a couple questions about these points. So if we're thinking about points on the polar plane in general, the first question we want to ask ourselves is, will each pair of polar coordinates define a unique point? In other words, when I'm looking at this pair of polar coordinates, is there any way it could define a different point for me? And right here, the answer is, of course, no, it can't define another point. So each pair of polar coordinates will define a unique point, and we can say yes, right? One rotation and one distance defines one point. Now, right here, the second question we want to ask ourselves is, will each point be defined by a unique pair of polar coordinates? Is this ordered pair the only ordered pair that's going to take me to this point, right? Could this point be defined by some other ordered pair? Right here, what we'd say is each point will not be defined by a unique pair of polar coordinates, because right here what we could say is that a rotation to the opposite direction and a negative r value are basically going to take me to that same point. So right here, if I had a negative 4, right, and a rotation of pi over 2, then basically I would be rotating pi over 2, but traveling in the opposite direction for, which would take me to the same point. So right here, we would say no. Each point, each point be defined by a unique pair of polar coordinates. No, each point will not be defined by a unique pair of polar coordinates. And we could say a negative r and a rotation in the opposite direction defines the same point. And as a matter of fact, what we've seen is our rotations can be greater than 2 pi or 360 degrees. So not only will a rotation in the opposite direction and a negative r value take me to the same point, I could have an r value of 4 and a coterminal angle to 3/2 pi, let's say 7/2 pi. And that pair of polar coordinates would also take me to the same point. It would be a full rotation around and then back 3/2 pi again, and then that same direction, it's going to take me to that same point. So also, or any coterminal angle. So right here, what I want you guys to do is to go ahead and find 2 ordered pairs that are going to take you to the same point as B and C. One that will give one with a negative r value, right, or an opposite r value, we should say. So we're looking for one with an r value of 2 for our B, and then one with the same r value. So 2 polar coordinates that will give you the same point as the polar coordinates that B and C give us. So we'll pause the video and give that a shot. Okay, so looking at B and C right here, we could say that the ordered pair 2, 330 degrees would take us to that same point. So of course, if we rotate all the way around 330 degrees, and then we have a positive r value of 2, we would get to that same point. Similarly, right here, we could say that a rotation of 510 degrees would be a rotation all the way around, and then back to that same terminal side. And then a negative r value of 2 would also take us back to that same point for B. Right here, if we're looking at C, we can say first that a rotation of 5/3 pi would be a rotation in the opposite direction. And then right here, our negative 3 would take us backwards 3 to our point. Let's pull that down a little so we can see that. Backwards 3 to our point. And then also, if we had a rotation of 2/3 pi, that would just be this rotation right here. That's coterminal to 8/3 pi. And then right here, that positive length of 3 would take us to that same point as well. All right, so in general right here, let's say we have a point r theta. We want to think that we could have an ordered pair that would define the same point if we had an r value with any coterminal angle to theta. So we know coterminal angles differ by 2 pi, increments of 2 pi, so we could say 2k pi, theta plus 2k pi, where k is an element of the integers, would give us a coterminal angle, and that would give us, of course, the same point. Similarly, if we had a negative r, we could say a rotation that takes us in the opposite direction, so that would be a rotation plus pi or plus 180 degrees would take us in the opposite direction, or any coterminal angle to this. So right here we could say plus again 2k pi, right? So actually we've come up with just 2 examples here that will take us to the same point, but really there are infinite examples, and actually we could represent this second point a little bit in a form that's a little bit more simplified. We could say this would be theta plus, and then right here we could say 2k plus 1 pi. So really infinite polar coordinates can define the same point. All right, so this is the end of this first video. We're going to stop this video here and move on to the next video, which is going from rectangular coordinates to polar coordinates and from polar coordinates to rectangular coordinates. All right, so see you on video 2.